We introduce our work GANs Spatial Control via Inference-Time Adaptive Normalization. This is a joint work of Karin, Jakoel, Liron, Efraim, and Tamar, Rott, Shaham from the Technion. Nowadays, GANs are an important building block in many image editing and manipulation algorithms, mainly due to the high visual quality of the generated images. Most of the approaches achieve the desired effect by manipulating the latent code. However, since many current GANs models map a latent vector that has no notion of spatial coordinates into a two-dimensional image, any manipulation of the latent code affects the whole image, causing a global manipulation effect. We suggest a new spatial-aware normalization technique that is applied on pre-trained GANs at test time only and enables spatial control over the generation process without any need in additional training. This allows a variety of applications that modify only specific image regions. For example, randomly generating sub-regions within an image while keeping the rest of it fixed, transferring local attributes from one image to another, controlling the saliency of different objects, and modifying a specific part of the image to belong to a different class. All these are done using a pre-trained GAN without any further modifications or training phase. In common GANs models like BGAN and StyleGAN, the latent code is embedded into the generation process through the normalization units. Namely, the denormalization parameters directly depend on Z. Those parameters are duplicated along the spatial dimensions and affect the whole image. So any change in Z causes a global effect in the image space, without control of the manipulation effect across different spatial locations. We suggest a simple modification. We allow the normalization operation to vary spatially. Instead of letting only a single latent code to govern the whole image, we are able to blend several different latent codes according to a guidance map to control the generation at different regions. We perform this adaptation at test time and thus can use pre-trained GAN models with no additional training. Let's see some results. First, using our Inference-Time Adaptive Normalization, we can randomly resample only specific regions of an image. In these examples, we first generate images using StyleGAN and then randomly regenerate only a specific part of the face. By doing so, we are able to create new image content. For example, new eyes appearance, nose shapes, lips, and chin composition, while keeping the rest of the image intact. The next application is attribute transfer. Here, given a source latent code, a target latent code, and a mask, we generate an image that corresponds to the attributes encoded in the source outside the indicated area and in the target inside. The effect is that we are able to transfer only local attributes like lips, eyes, and nose appearance. This is in contrast to the original style mixing by StyleGAN, where we get a global mixing effect. The next task is class hybridization. Here our goal is to generate images that combine two different classes. We use BGAN that was trained to generate images from only one indicated class at a time. Given two latent vectors of two classes and a mask, we are able to generate an image that combines the classes according to the mask. The last application is saliency manipulation. Here we would like to edit an image such that a specific region will be more salient. We do so by finding the optimal transformations of the latent code inside and outside that region using our technique, such that the saliency map of the generated image will obey the desired manipulation. Note that our approach can generate completely new image content like the house in this example. To conclude, we introduced a new normalization technique for spatial control over the generation process in GANs, which is applied at test time and could be used for a variety of applications. Thank you.